Welcome to True Projects. In this video, we are going to explain about the project entitled as a portable real-time electronic nose for evaluating seafood freshness using machine learning. So before getting into the video, let me give you the brief description about the project. A portable real-time electronic nose is a smart device designed to detect and analyze orders released by seafood as it spoils. By using gas sensors and machine learning algorithms, it can identify freshness levels quickly and accurately. This technology offers a fast, non-destructive, and reliable way to ensure seafood quality and safety. Coming to the abstract, seafood freshness plays a vital role in ensuring food safety, maintaining quality, and meeting consumers' expectations. Convolutional methods used to access freshness, such as sensory evaluation, chemical tests, and microbiological analysis, often have limitations because they are time consuming, subjective, and requires specialized laboratory setups. This project addresses these challenges by introducing a portable real-time electronic nose system combined with machine learning for efficient freshness evaluation. The system employs an array of gas sensors to detect volatile organic compounds emitted as seafood begins to spoil. These sensor signals are then analyzed using machine learning algorithms to accurately classify freshness levels in real time. Due to its compact design, low cost, and easy to use, the proposed system is well suited for on site applications such as fisheries, seafood markets, and supply chain monitoring, helping to improve quality control and reduce food wastage. Coming to the existing system, in the existing system, seafood freshness assessment relies mainly on sensor evaluation, chemical analysis, and microbiological testing. Sensor analysis involves human inception of odor, appearance, and texture, which depends on expert experience and is highly subjective, often resulting in inconsistent and unreliable outcomes. Chemical methods such as total void basic nitrogen and pH testing provides more precise indicators of spoilage but requires sample destruction, skilled personnel, and laboratory grade instruments. Similarly, microbiological analysis offers accurate freshness and safety evaluation by measuring bacterial growth, yet it is expensive and time consuming, often taking hours or days to obtain results. Due to these limitations, existing methods are impractical for real time and on site monitoring, making them unsuitable for fast paced seafood supply chains where quickly freshness decisions are essential. Coming to the proposed system or base paper work, the proposed system presents a portable electronic nose integration with machine learning to provide a fast and reliable solution for seafood freshness evaluating. It consists of an array of gas sensors designed to detect volatile organic compounds released during seafood spoilage. The sensor signals are continuously collected and pre-processed to remove noise and extract meaningful features. These features are then analyzed using machine learning algorithms such as support vector machines, random forest, or neural networks, which have been trained to recognize different freshness patterns. Based on the analysis, the system classifies seafood into fresh or spoiled categories in real time. The proposed approach is non destructive, cost efficient, and user friendly, eliminating the need for laboratory testing and expert judgment. Due to its compact and portable design, it can be easily deployed as fishing docks, processing units, cold storage facilities, and retail markets for on site freshness monitoring. Coming to the dataset, the ENOS based fish freshness evaluation dataset contains sensor data collected using a gas sensor electronic nose system developed to analyze and classify seafood freshness. The dataset consists of estimated gas concentration values measured in parts per million, which are derived from raw analog outputs for multiple gas sensors, typically MQ series metal oxide sensors. These sensors detect volatile organic compounds released as seafood undergoes spoilage. The recorded sensor values act as an input features for machine learning models, enabling pattern recognition and freshness classification. The dataset includes samples from various seafood types such as salmon, shrimp, crab, cod, and tuna, allowing the model to learn diverse spoilage patterns. Due to its structured sensor data and variety of seafood samples, this dataset is well suited for deploying and validating portable real-time seafood freshness evaluation system using machine learning techniques. Coming to the novelty or extension or enhancement or improvement. As an extension, a voting classifier was applied to all 5 individual seafood datasets, achieving 100% accuracy for each. Additionally, when all 5 datasets were combined into a single dataset, the voting classifier still achieved the highest possible accuracy of 100%, demonstrating its strong performance in classifying seafood freshness across multiple types. For regression task, a voting regressor was implemented on all 5 datasets, achieving R square of 100% and RMSE of 0.4%, indicating highly accurate predictions of spoilage related values. When the datasets were combined into one, the voting regressor produces the low error rate RMSE of 0.07% with R square of 100%, confirming its effectiveness in modeling spoilage trends across diverse seafood types. All existing and proposed models were also built for comparison. Additionally, to interrupt the machine learning predictions, explainable AI techniques such as Lime and SHAP were employed. These methods help identify the most important sensor features influencing the freshness prediction, providing transparency and understanding of the model's decision making process. Furthermore, a user interface was developed using the Flask framework, allowing users to input sensors data and obtain real time predictions from the trained models. This makes the system practical for on site seafood freshness evaluation, bridging the gap between advanced machine learning models and real world application. Coming to the flow of the work, we have both classification and regression. First, let us check for classification. First, we have importing the packages. Necessary Python libraries are packages. Necessary Python libraries and packages for data pre-processing, visualization, and model building are imported. Next, exploring the dataset. The seafood freshness datasets are examined to understand the structures, features, and types of seafood included. Next, label encoding. Categorical or string data is converted into numerical integers for machine learning compatibility. Next, feature selection. The predictive power score method is applied to select the most relevant features for predicting seafood freshness. Next, data visualization. Visualization techniques such as correlation matrix are used to analyze feature relationship, particularly for extinction data sets. Next, data split. The dataset is divided into training and testing 80:20 sets for model evaluation. Next, build the classification models. Models are built for each of the 5 datasets separately using AdaBoost, Random Forest, XGBoost, Decision Tree, Navy Bias, Gradient Boost, KNN, and as an extension, a voting classifier is applied, combining Random Forest plus Decision Tree along with soft voting. When combining all 5 datasets, SMART is used for handling imbalance, standard scalar for normalization, and models are retrained including the voting classifier. Next, training the model. Models are trained on training data for accurate predictions. Next, comparing the models. Models are evaluated using accuracy, precision, recall, F1 score, and cross-validation accuracy. Next, comparison graphs. Graphs are generated to visually compare the performance of the extension models across different metrics. Next, save the best trained model. The model with the best performance is saved for later deployment. Next, explainable AI visualizations. Techniques like Lime and SHAP are used to explain which features most influence the prediction. Coming to the regression flow, first we have importing the packages. Required Python libraries for regression analysis are imported. Next, exploring the dataset. Datasets are examined to understand features and trends related to seafood spoilage. Next, label encoding. Categorical variables are converted into integers for regression models compatibility. Next, feature selection. PPS methods is applied to select the most predictive features for regression tasks. Next, data visualization. Correlation metrics are plotted to understand relationship between the features. Next, data split. The data is divided into 80% training and 20% testing sets. Next, build the regression model. Regression models are built for each dataset using Decision Tree, XGBoost, AdaBoost, and KNN. As an extension, we have applied voting regressor. When combined, all 5 dataset, Decision Tree, XGBoost, and voting regressor models are built. Next, training the model. Models are trained on training datasets to predict spoilage related values. Next, comparing the models. Model performance is evaluated using R-square score, RMSE, and CVMSE. Next, comparison of graphs. Graphs are generated to compare the performance of regression models, especially for combined data sets. Next, save the best trained model. The best performing regression model is saved for deployment. Next, explainable AI visualizations. Lime and SHAP are used to identify which features most influence the regression predictions. Coming to the front end, a user interface is built using the Flask framework with user registration and login functionalities supported by SQLite. The front end integrates the trained model to make predictions based on user provided data. Users enter feature values related to seafood freshness. The input data is pre-processed to match the format accepted by the trained models. The pre-processed input is passed to the trained machine learning model for prediction. The prediction freshness or spoilage level is displayed on the front end in the real time for the user. The algorithms used are, for classification, we used AdaBoost, Random Forest, XGBoost, Decision Tree, Navy Bias, Gradient Boost, KNN, and as an extension, we have applied voting classifier with RF plus DT soft voting. For extension, we have combined all 5 datasets. We have used mode, standard scalar, random forest, decision tree, Navy Bias, voting classifier, which combines random forest plus decision tree soft voting. Coming to regression algorithms, we have used decision tree, XGBoost, AdaBoost, KNN, and as an extension, voting regressor. When combined all 5 datasets, we have used decision tree, XGBoost, and voting regressor. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework Anaconda, primary language Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is the complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contain the algorithm information which will be loaded into the project code during the runtime. .ipynb files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome, so that the home page of the project should now be displayed in the browser. This is the front-end build using the Flask framework. In this page, we have Home button and Join Project button. Firstly, click on Join Project button so that the create account form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and sign up page will be open where you need to access the application with the help of username and password. Then click on sign in so that the home page of the project will be opened. In this page, we have home button, prediction button, graphs button, and notebooks button along with leave the project button, which means log out button. Firstly, click on prediction button so that the sensor's data input form will be open where you need to enter VOC sensor readings for freshness prediction. Here we need to enter the attributes like ammonia MQ 135 ppm, CO2 ppm, alcohol ppm, methane ppm, hydrogen sulfide ppm, LPG ppm, hydrogen ppm, and ammonia MQ 137 ppm. So let us enter the values and check the freshness, like whether it's fresh or not fresh. The values are being successfully entered. Now click on predict freshness so that the given inputs are pre-processed and the output is displayed as not fresh. The status is not fresh. Time to spoil is 18.0 hours. And we also have the quick info like storage temperature, safety levels, and best before. Here we have VOC analysis, risk assessment, and ML confidence score, along with some safety recommendations and storage guidelines like temperature and humidity. Now click on new prediction so that the form will be opened. Again, let us enter the values and check for the freshness or not freshness. The values are successfully entered and now click on predict freshness so that the given input values are pre-processed and the output is displayed as fresh. The freshness status is fresh and time to spoil is 0.5 hours. And here we have the quick info of storage temperature, safety level, and best before. And we also have VOC analysis and risk assessment and ML confidence score, along with some safety recommendations and storage guidelines like temperature and humidity. Now click on graphs button so that the graphical representation of the project will be opened. As we are dealing with classification and regression, first let us check with classification graphs. In this, first we have seafood freshness classification outcome graph. The bar chart shows the result of a seafood freshness classification. There are significantly more fresh samples than not fresh ones, indicating that the dataset is dominant by fresh seafood. Next, we have top 8 predictive features graph. The graph ranks the top 8 sensor features based on their predictive power score. For classification, ammonia MQ137 is the most influential feature, followed by LPG and hydrogen, indicating these gases are key indicators in the model's prediction. Next, we have balanced seafood freshness for COD data classification outcome graph. The bar chart shows a balanced classification outcome for COD freshness seafood. Both fresh and not fresh classes have nearly equal sample count, indicating efficient data balancing and reduced class bias. Next, we have confusion matrix graph. The heat map shows the correlation between different gas sensor readings. Strong positive correlations are observed between methane alcohol and LPG hydrogen, while hydrogen sulfide shows weak or non-zero correlation with most sensors. Next, we have confusion matrix graph. The confusion matrix shows the performance of the freshness classification model. Most samples are correctly classified as fresh and not fresh, with very few misclassifications, indicating high accuracy and reliable model performance. And next we have accuracy by model graph. The bar chart compares the accuracy of different machine learning models used for classification. Random forest decision tree and voting model achieves nearly perfect accuracy, while Navy Bayes perform noticeably low. Next, we have precision by model graph. The bar chart shows the precision scores of different machine learning models. Random forest decision tree and voting model achieves the perfect precision, while Navy Bayes has a slightly lower precision, indicating more false positives. Next, we have recall by model graph. The bar chart compares the recall performance of different machine learning models. Random forest decision tree and voting model shows perfect recall, while Navy Bayes has much lower recall, meaning it misses more true cases. Next, we have F1 score by model graph. The bar chart compares the F1 scores of 4 machine learning models. Random forest, decision tree, and voting model achieves perfect performance, while navy bias performance noticeably worse with an F1 score of around 0.59%. Next, we have CV accuracy by model graph. The graph shows cross-validation accuracy of different machine learning models. Random forest, decision tree, and voting models achieve perfect accuracy, while navy bias performs lower with an accuracy about 0.69%. And next we have explainable AI SHAP graph. This SHAP summary plot shows how each feature influenced the model's prediction. Points to the right increase the prediction, while points to the left decrease it. And the color indicates feature values from low to high. Low indicates blue, high indicates red. Now, let us check with regression graphs. In this, first we have top predictive features for regression graph. The bar chart shows the top sensor features ranked by their predictive power in a regression model. Ammonia MQ137 has the highest predictive scores, making it the most influential features. Hydrogen sulfide, hydrogen, and LPG also contribute strongly, while methane, alcohol, and ammonia MQ135 have moderate impact. CO2 appears to have little or no predictive importance compared to the other sensors. Next, we have correlation matrix graph. The heat map shows correlation between gas sensor features where values near 1 indicate strong positive relationship. Methane and alcohol has the strongest correlation, followed by hydrogen and LPG. Hydrogen sulfide has generally weak correlations, while several other sensors are strongly interrelated. And next we have actual versus predicted values graph. The scatter plot compares actual versus predictive values for voting regressor model. Most point lies closely among the diagonal lines, indicating strong agreement and high prediction accuracy. A few scattered points shows minor prediction errors, but overall the model performs very well. And next we have RMSE by model graph. The bar chart compares RMSE values of different machine learning models. The voting regressor has the lowest RMSE, indicating the best performance, followed by the decision tree. XGBoost shows the highest RMSE, meaning it performs slightly worse compared to the others. Next, we have R-squared score graph. The bar chart compares the R-squared score of different models. All models shows very high R-square values close to 1, indicating excellent predictive performance. The voting regressor appears to perform slightly better overall compared to decision tree and XGBoost. And next we have CVMSC by model graph. The bar chart compares cross-validation across different models. The voting regressor has the lowest cross-validation MSC, indicating the best generalization performance. Decision tree and XGBoost show slightly higher errors, with decision tree being the highest among the three. And next we have explainable AI SHAP graph. The SHAP summary plot shows how each feature impacts the model prediction with higher SHAP values, indicating stronger influence. Hydrogen sulfide, hydrogen, and ammonia MQ137 has the largest impact, while CO2 contributes very little. The color gradient indicates feature values, showing how high or low sensor readings push predictions positively or negatively. And then click on leave the project, which means log out the project. So finally, this project successfully demonstrates a portable real-time electronic nose capability of accurately evaluating seafood freshness using machine learning techniques. By analyzing sensor response to volatile compounds, the system provides rapid, non-destructive, and objective freshness assessment. The proposed approach offers a low cost and practical solutions for improving quality control and food safety in the seafood industry. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.